All right, let's go with it here. So we're going to take a look at something called the fundamental theorem of calculus. And it's the stuff that we've been studying about all this time. We're going to connect everything together. There is also something called the fundamental theorem of arithmetic, fundamental theorem of calculus. And I don't know what makes it a fundamental theorem. I'm not sure. But it does connect a lot of different parts. And it is a lot easier to do part two first before we get to part one. It's just more understandable, I think, to the student mind. So let's go with it here. So if f is continuous on a to b, then that little integral that we've been studying, integral from a to b of f of x dx. It says that it's a connection between the derivative and the antiderivative. There it is. It's f of b minus f of a, where the derivative of capital F is really little f. So technically, big F is the antiderivative, but not including c.
Oh, great. I had to wrote this down. It says dx dy.
dx dy. Oh, wow, okay. So let's go with the one we have already done before. Don't have to do it again, but there it is. Remember how we got what is the area of x squared from 0 to 1? And we said, hey, it is 1/3. So then the question is, hold on.
Third over 3, which equals 1/3 minus 0.
So let's connect just a few pieces together here. So that we know already, right? We did it by rectangles, making them go to infinity from the left side, right side. And so now we put this together. So that means the area underneath this curve should be 1/3. So let's do it with the fundamental theorem of calculus. But let's handle the c issue first. Let's kind of handle that. So technically, what is the antiderivative of x squared? It would be capital F of x would be x to the third over 3 plus c. Is that true? Okay. So here's what we got. If we're going to evaluate and we're going to subtract b to a, that c is going to be subtracted from itself. So we'll do it the first way, easy way, then we'll do it with the c values decided. Let's go. Number 3. Here's where we really start. And let's see if I can push this little thing away. Kind of in the way a little bit here. Find the area of this guy from 0 to 1 of x squared. So let's do it by the fundamental theorem of calculus. And we'll add some notation here too. All right. Got 2 pages and 40 minutes. So I would write it like this: the antiderivative, or the integral from 0 to 1 of x squared dx. Because the x variable is the one that we're dealing with. Question comes up, do we ever deal with the y variable? Yes, it totally will be that we sometimes integrate along the y-axis as opposed to the x-axis. Fun stuff like that, but let's go with it. So here's what we do. We're going to take the antiderivative, not including the c value. We're going to say x2 plus 1 is 3 over 3. Some new notation. Here it is, evaluated from 0 to 1. So it's the same exact stuff that we had. Now, different books will use different notation for this evaluation bar. But we'll deal with it in just a second here. According to the second fundamental theorem of calculus, here's what we'll do. We plug in the 1 into the x, and then we subtract from plugging in the 0 into the x. True, right? This is f of b minus f of a. And do we get the answer?
Yes.
Absolutely. We get 1/3 exactly the way we wanted it. Perfecto. Okay, so let me do a little bit of extra work here. The fundamental theorem of calculus really does this, though. It says, hey, look, if you go from a to b, or from, let me actually change it up. Let me put numbers in here. From 0 to 1 of 1/2 x dx. And then let's put in the c value that's already here. So this would be x cubed over 3 plus c. True? 0 to 1. We don't know what c is. I don't know what c is. But if we do this, what's going to happen with the C value when you do that? It's going to cancel out. That's exactly what the fundamental theorem of calculus says. You're going to get a plus C minus C, and they're just going to go away anyways. So why write it down if it's going to disappear anyways? Cool. All right, some notation. Notation off the side. So either this one, it's either a bar line going from A to B, or some textbooks will have it like this. They'll go from 0 to 1. It's almost like end of a bracket. And mathematicians debate like which one's the right one. Don't know. Okay, are we good there?
You're right.
All right, so now let's start. So again, just using the second fundamental theorem of calculus, we are just getting area underneath the curve. And if you ever want to, use a calculator. Just graph it what it looks like. Remember, areas could also be negative. Areas could be 0. There's like a lot of different things you can do here. So let's go with it. All yours. Try it yourself first. And then I will help out a little bit here. So I'll give you a minute. Do it yourself.
It's just one,
The answer?
maybe.
No.
Because or no. Just that's right. We're taking the antiderivative, not the derivative.
Cool.
Yes.
All right. What do you come up with? Or close to 3 is perfecto. So the 1 turns into an X. This turns into over 4. Is that right?
Yeah.
And that's why you have the little brackets sometimes right here. So notice it kind of keeps all that together. And so if you have more than one term inside there, usually the brackets is what it uses to keep all that insulated. But you already got the right answer here. So let's go. 2 plugged into that. It gives you 2 plus 2 squared over 4 minus, and zeros you're going to learn how to love. Because they just love zeros.
Daughter who I was in the first one.
Mm-hmm. Cool. So then at that point, it's 2 plus 1 makes 3. Dun, 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 dun. Sweet. Okay, so that means the area of that would be 3. Okay, of course we got to do trig functions here. That's the fun part about it here. So trig function, we're going to go from pi to 2 pi of cosine theta. Ooh, look at that. It's not dx anymore.
Okay.
It's d theta. Still, it fundamentally works exactly the same way. So all yours. I just didn't think about what is the antiderivative of cosine.
Well, I'm thinking that the entire thing is just 0.
Oh, cool. Yep, I gave you a little graphic over there as well. Here's a cosine curve, right?
Mm-hmm.
Starts off with 1, goes down to -1, comes up to 1. And so if we do plot only from pi to 2 pi, yes, these guys are exactly the same. So let's see how they zero out on each other. So let's see, if we undo that, notice it's just that right there, right?
Mm-hmm.
It's one term. And normally, again, one term is just an evaluation bar as opposed to a bracket.
So that just means 0 minus 0.
Mm-hmm. Sine of 2 pi minus sine of pi, which really is just 0 minus 0. Notice that the numbers turn out to be correct, right? The number at the end, but it doesn't give you the area itself, right? It wasn't the area of 0 minus area of 0, right?
Right.
It was technically area of like 2 or something that then subtracted out to 2. So the numbers themselves don't carry the exact measurement of it. All right, a little more complicated trig function. I know you can handle it. Dun, dun, dun. 0 to 2 pi over 4 of secant theta times tangent theta d theta. Now we got craziness going happening.
We're named little sheep. Hey, that's the derivative. There it is. Yes, secant.
Perfecto. Yep, the antiderivative of secant theta tangent theta is secant theta. Evaluate from 0 to 1. Now, notice the little brackets there?
Yeah.
Again, brackets or evaluation bar, it doesn't matter. This one's just a one term, still put a bracket bar. So some textbooks, just to be consistent, they just always put a bracket bars here. And sometimes they're super consistent, they'll put a bracket bar here. Always, always. Doesn't matter, just how your preference is. I will knock down points for it here, but let's put it in. Secant of pi over 4, subtract secant of 0. And secant of pi over 4, that is the reciprocal of cosine. And that's root 2 over 2. And the flip of it would be root 2. And secant of 0
Yes. Is 1/1.
is just 1. Perfecto. There it is. So the area is actually root 2 minus 1. True, true. That is it. Whatever that value is, but let's see. Root 2 is about 1.4, right? Subtract 1, so about 0.4-ish. But this one actually gives us exact value. That's the important part there. All right, trig functions, check. Let's go some next one here. This one, see if you can figure that one out.
Oh, wait.
It's a tricky one, but tell me, what do you get for the antiderivative?
Let's see. I don't think there is an antiderivative.
Chasaroo. Okay, so take a look at your sheet of all derivatives and
Oh,
then see if you can
never
go
mind. It
backwards.
is the ln one.
Perfecto. Yep, it's ln, right? The derivative ln of x is 1 over x, or a derivative absolute value of ln of x, right? Because there's no such thing as taking a value of a negative of it. So ln of absolute value of x, bracket 3 to 4. Now, the only thing you have to be careful for here, just to be mindful of the fact that you wouldn't be able to go from negative numbers to positive numbers, right? From 1
Right.
over x, because you have a break in the graph and then you get some weird stuff. Okay, so these guys do have to be continuous to work.
Mhm.
All right, let's plug it in. So ln of 4 I got minus ln of 3. And can you write that in any simpler form? Ooh. Even though that's correct, ln of 4 minus ln of 3 is correct. Is there more?
Look at my rules.
Yep, there we go. ln of rules or log rules.
Oh, it's ln of 4/3.
Perfecto. ln of 4 over 3 is done. There it is. Now, both are correct. Both will be accepted on test. This one is a more condensed form. Okay, let's get going some more. Let's go with a little bit more difficult one. So this one you have to figure out. Ooh, what? I give answers? No, no, no. I can't give answers. Gotta go like this. Come back over here. I might have done a few things wrong. Let's see. But woof. E. 0 to 1. Okay. Whoa, that's crazy. It's not a dx, it's not a d theta, not a du. And again, it doesn't matter. It's a dummy variable. You just work with whatever the value is. So that looks like a quotient rule to me, except we don't have any anti-quotient rules. Okay. Bummer. Super bummer. Okay, but so then I gotta simplify this as much as I can. I guess that's what I gotta do. Can I split the denominator into two different pieces?
Yes.
Absolutely. So let's go from 0 to 1. Sorry, 1 to 2. Split the denominator into 4 over u cubed plus. Tell me if you agree with that.
Mhm.
So
First
u
one
to
is
the 2. Uh-huh.
ln. And the second one's ln.
Second one's ln. Uh-huh.
This one is
Now, in your mind's eye, can you bring up the 3 up to the top, make it a negative u to the negative 3,
yes.
and do a power rule? That's what I want to do there.
Negative 8 divided by n squared.
I'm going to do it with you here real quick here. Let's see. So in my mind's eye, I'm thinking u 4 u to the negative 3, right?
Mm-hmm.
Which will then convert into u to the negative 2. Is that right?
Right.
We're adding 1 to it and dividing by that 1.
Mm-hmm.
All right, so I got myself a
Negative
bracket.
2.
So negative 2. And then I'm going to send that u to the negative 2. I'm going to send it back down to the bottom because I hate dealing with negative exponents. Perfect. I think I got that one taken care of. And then it's plus, right? Plus ln, absolute value technically, but we know we're going to get positive values from the absolute value. All right, can we finish it up from there?
You could split these up, right?
Oh, that's true. Yeah. If you wanted to, you could split them up in two different pieces. You can think of it as a whole. So you can plug in either the 2 into all this, or you can split off individually. Probably just keep them individually here. So it would go like this, plug in a 2 into that, makes 2 squared plus ln of technically 2, right? We don't even need subtracting off. A 1 goes in there now. There it is. And do a little bit of work here. That's 4. So that's what, a negative 1/2 plus ln of 2. Kind of careful here. That's 1. That's going to be a what? A 2.
Yeah.
Want to keep this in parentheses still just to make sure this is a negative 2 plus ln of 1. Then we can drop the parentheses. So 1/2 plus ln of 2 plus 2 minus ln of 1. Oof, okay.
You just add that and then to ln of 2 over 1.
Perfect. Okay, ln of 2 stays, ln of 1 is technically just 0, right? And then we have negative 1/2 plus 2. So 1.5 maybe, right? 3/2. So I got 3/2 plus ln of 2 as our final answer. Oh, we good with that?
Yes.
Awesome. We cool like that. Total fun. Okay. So notice what we had to do is we had to do a little bit of arithmetic, right? In order to get it, because there is no such thing as a quotient rule or anti-quotient rule. It may be, but we don't have one yet. Okay, next one. I'm gonna go 0 to 1 of this guy. There's my dx now. Okay, so a little bit of trouble. Tell me what you're thinking. As you do this here, we have no product rule. We have no. So notice there's kind of two things, right? There's x plus one, right? Inside or encased into a squared term. And we do a little bit of arithmetic too, or algebra to simplify it out.
Yes.
Absolutely. So a 1 plus x quantity to the second power is,
You can split them all up.
sure, yeah, I can split them up, or I can write them individually here. So 1 plus, what, 2x, is that right?
Plus x squared.
All in dx. Now, normally, if you split them off, that's cool, but normally we don't split them off because it's a lot easier to, first of all, not having to rewrite integral from 1 to 2, integral from 1 to 2. Second of all, it's a lot easier just to plug in the 2 into all of it, plug in the 1 into all of it, subtract, and be done.
But now you have to take the antiderivative.
Yeah, let's take the derivative, and then we're still going to do the derivative of each and every single one anyways, right?
X plus x squared plus x to the third over 3.
Okay, boom, 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 plus x to the third over 3. I agree with that, going from 1 to 2. And then can you finish it off from there? And then tell me when you get the answer.
Six and a third.
Okay, let me just check here my work here. That's 2, is that right?
Yes.
That's a 4, and that's going to be
8 thirds.
8 over 3. Subtract a 1 plus a 1 plus a 1/3. Ooh, now this could be a little bit crazy here. So let's put that's going to be a 6 plus 8 over 3. I'll handle the 3's individually. I'm going to subtract 2, subtract a 1/3. Are we okay with that? So then I got myself 4. Let's see. 6 minus 2 is 4. Is that right? 4. And then we got 7/3. Now we get common denominators. And then I'm going to wind up.
7 thirds.
Gotcha. Okay. No problem. So I got 5/3 on my hands. Let's finish that off. And then we'll handle Q. All right, two ways this can break down. I already mentioned one of them here, but let's do this one. So the next two you will not be able to do, but you tell me why you can't do them. So state what is wrong with the
You
equation.
told me that you can't go from negatives to positives.
Perfect. Okay, so first things first is you cannot go through somewhere where there's not continuous functions here. So 1 over x is not continuous. Exact that x equals 0. So you cannot go through x equals 0. We good there? So given a graph of this guy, what does not continuous mean, right? There's my x squared term. So there goes.
This. Oh, yeah.
Perfect. Yeah. So here's our problem right there. You cannot go through vertical asymptotes, right? At that point, because it's gonna break on you here. So be careful sometimes. In the book, you'll do one, and then at the end you'll look and be like, oh, not possible. Like, oh shucks, that's right. All right, there's another one here. What is wrong with this?
There is a break. Wait. I'm guessing what's one of the cosine square. Secant square x. Oh yeah, because it goes. It's a little woogly thingy that goes.
Woo
It
thingy.
goes all the way up.
Yes, So this one actually, I think, has two problems, but let's take a look at the second problem. First things first, tangent. If you look at a tangent problem, it has a break at pi over 2, which is exactly inside here, right? Between 0 and pi. Okay, the other one is this. If you think about it, look at your notes and you can think of, can you see any one of your derivatives where you get to the derivative of tangent?
No.
Yeah, there is no antiderivative tangent so far. We haven't found one yet. We good? So there is no, let me see if I can write it here. There is no known, I'll say known because we might know it later. Known. And notice if I don't put any numbers to it here, right? We don't know that, right? We can't go backwards on tangent as of yet. Okay, jamming. Okay, that was part 2 or the second fundamental theorem of calculus. That's what it is. You can find areas based upon just taking the antiderivative, subtracting, and done. Then there's the first part, which I think is a little bit more complicated. Part 2, if you want to write it down, there it is. It says, part 1, sorry. If f is continuous on a to b, then the function g is, and then there's a interesting thing that I'll let you guys write it down.
You guys.
All of you guys. Oh, I'm going to just check if I did it the long way, just to kind of verify stuff here. Yeah, okay. I did this the long way, and then we're going to do it the short way. Then, and this is the easy part here. You understand this? So it says this. This is a kind of interesting thing. If you're going to take g of x, which is going to be the antiderivative from a, which is a constant, to x, which is a variable, of f of t dt. And again, why is it a tu over here? Why is it x? Just to make them distinguished from one another, right? The f of t and the dt have to go together because you're taking the antiderivative of the function of t. You're going from a to b. A to b we know is continuous. So then the question is, what's the derivative of g of x? And we're saying the derivative of g of x will just be whatever f of x. And notice what we do is we plug in the variable at that point. So we're trying to connect two functions now together. We're trying to connect g of x, f of x is a function, and the derivative of g of x all together at one piece. Okay, so let's do this here. Let's do it the long way first, and then we'll see how that all comes about, and then we'll do it by the fundamental theorem of calculus. So let's go with this here. So find the derivative of g of x. If g of x is the antiderivative from 4 to x of x squared. So let's go through this one together. So if we did this according to the second fundamental theorem of calculus, this would be x to the third power over 3 evaluated from 4 to x. So then what we do is we plug in the x into it. So we got x, 3 of that, plus, oh boy, this will be fun, 4 to the third power over 3. Now I subtract, right? Oh, okay, sorry, it's subtraction, right? Got a little ahead of myself here. Okay. All right, let's just get a number for this here. 4 times 4 times 4, 16. 16 times
2, 21, and 3. 21.
Oof. Okay. Just off the side, just real quick, if that's 16 times, should be 64. Is that right? Yeah. I just want the number on top here. That's fine. Okay, are we good there? So then we got x cubed over 3 plus 64 over 3. But then the question is this, what would be the derivative of that? Let's see if I got some. Ooh, minus. Thank you so much. Still keep on forgetting the minus here. I want to be adding stuff here. Okay, minus 64 over 3. Boom. Okay. So then let me bring it up here because I'm running out of space here. Now what I want, because this is g of x, right? G of x is x cubed over 3 minus 64 over 3. But then the question is, what's the derivative of g of x? Ooh, that's from a long time ago. That's chapter 3 stuff.
X squared.
It's x squared, which is exactly the same function we began with in the first place.
Yes.
So there's the connection between antiderivatives and derivatives in a straight functional way. That's what it is. Okay, so question is, what's the antiderivative? You can go straight on through. You can just say, oh, the answer is this. Again, we're taking the derivative. We're seeing what the variable is at this point. And we're saying that is the answer. Okay, it's just the functional aspect of the function out right inside the derivative. Okay. Bam. I'll let you do one here or two. We'll see. So using the first fundamental theorem of calculus, can you give me this? What is the derivative of that?
So first. Just take the derivative. This is the antiderivative.
But remember, you're just going to use the first fundamental theorem of calculus, right?
Right.
Saying the derivative of this is, and then you just state it. Should take you 10 seconds.
It's just 1 plus square root of x. Right?
Yeah, the only thing you got to be careful for is what variables you're using and what variables are there.
Okay.
In case the connection here is you're taking derivative with respect to x, but then you're also taking it to the x function, right? Yep. No, that's where it comes like, hey, it's too easy. It's too easy. But we already proved it on that side here. So then this one is very, very similar to the first fundamental theorem of calculus. Notice the t's are there. I just changed the function. I have, so given that, find the derivative of f of x. So again,
1 plus
give me
x to the 4. Square root 1 plus x to the 4.
perfecto. If you got that and you understand where that came from, you are doing great. Cool. Man, that's awesome. 5.3, we are done. We covered the second fundamental theorem of calculus, which deals with areas. And then the first fundamental theorem of calculus, which deals with the functional connection of derivative and the antiderivative. Sweet. And we've been cool.